Yes. So this is, I think, day 7, if I'm not wrong. Yeah. So let us start this particular session. In this particular session, our main agenda will be discussion of our FPGA part number. Like, what do you mean by an FPGA part number? And also we will classify the FPGAs, right? So let us start this particular session. First of all, we are only focusing upon Xilinx part numbers because we are going to work with Xilinx board, right? So I'm going to discuss about this Xilinx part numbers, right? So basically, a Xilinx FPGA part number is not random number, and it is precisely going to tell you like what type of FPGA family it is, whether it is RTX or whether it is Zing. Okay, and it is also going to tell about the logic density, like how many LUTs you are going to have, and what is the package type, and what is the speed grade and temperature grade, right? So if you understand the part number, we already will come to know the 80% of the device capability even before opening the data sheet, right? Now, what is this part number? So as I told you in the previous session also, this part number is, it's like a unique identity each FPGA is going to have, right? So that is what we are going to see. Yeah. So this is one of the example of how a part number is going to look like. So you can see this part number on a simple FPGA chip. Whenever you have a FPGA chip on this particular FPGA chip, you can see this part number written, or else you can also see this part number written on a data sheet. Okay. Or else if you are purchasing that particular FPGA, you can also see that particular part number on the specifications or on the board or the box which it has been. Okay. Now, so first one is vendor specific. So this XC we have, right. So this XC indicates it is Xilinx commercial device. And this second part, this is basically XC will tell you which vendor it is, and the 7A will tell you the generation. Okay, so 7 represent 7 series FPGA architecture. Okay, and the third one is family and architecture, family and density. A35T we are having, right. So basically, it will show you the RTX family in the transceivers with the transceivers. And this -1 is nothing but my speed, how much speed and what is the performance level. And the fifth thing is packaging level, and followed by temperature grade. Okay. So this is how we are going to divide a part number. And this is not mandatory that you need to know this completely. Just you need to have an idea like what is this part number is basically telling you, right? So this is in more detail, like XA stands for the commercial standard Xilinx commercial device for general purpose. And you also have something known as XA. So if you have in your part number like XA written, it basically it is for automotive grade devices with enhanced reliability, right? And XQ, there is something also known as XQ. So if there is XQ in your part number, then it is for military and space grade for extreme environments, right? So this is how you're going to categorize your part numbers depending upon whether it is commercial or automotive or military, right? And this prefix will indicate the device qualification and reliability level for different application requirements, right? And how to choose this part number, that and all we are going to discuss when we are going to learn about Vivado tool. Okay. Now, next is FPGA generation and family. Okay. So, for example, the generations we have Spartan 6, RTX 7, Ultra Scale Plus. These are the generations which we have in our FPGAs. And A stands for RTX, which is a low power FPGA. K stands for Kintex, which is a performance FPGA. And V stands for Vertex, which is a high end FPGA. And Z stands for Zinc. Like if you have here this A, okay. So for RTX FPGAs, you are going to have here A, and let's say if you are going to have XC7Z, then it is for zinc-based FPGAs. Okay, and if you are going to have XCV, it is for vertex-based FPGAs. This is nothing but different type of families. Okay, and this will all come under Xilinx family only. And in Xilinx family, we are going to first of all categorize our vendors and devices, and after that we are going to categorize our families. Okay, up to here is it clear? Are you following me? Anyone needs the explanation again? I think most of them are freshers, so that's why I'm again reconfirming. Yes. Any queries over here? Shall we move forward? I hope it is clear, right? Yeah. Now, so next is speed grade. Okay. So -1 is basically standard, and -2 is very faster, and -3 is maximum clock frequency and timing performance. So as you're going to increase this particular number, your clock frequency and timing and the speed grade is going to increase. Okay. So the lower the number indicates the faster the device. Okay. So -1 is low or -3? -3 is low. Which number is low? -1 or -3? It's a basic question. Yeah, -3 is low. Okay, exactly. Okay, so lower the number here, the speed is going to increase, right? So yeah, so speed grades affects the maximum clock frequency and timing closure. Okay, so we'll see what is your clock frequency and where you are going to get your clock frequency and who is generating the clock on your board. Those are all things we are going to see. Okay, just you need to have an understanding of what is your part number and what it is indicating. Okay, so the very first one is vendor, and next is family, and next is speed grade. Okay, and next comes the temperature. Okay, so what is this temperature? C stands for commercial, and this is a temperature rating, and I stands for industrial, and Q stands for automotive, and M stands for military. So we have over here, right, this C. So this is our temperature ratings, right? So it is going to mention you what is the temperature rating it is going to have. Okay, whether it is commercial or whether it is industrial or whether it is automotive or whether it is military. Okay, so this is what your part number is basically indicating you. Okay, so is it clear for everyone? Shall we move forward? It's some random example. I think it is Artix board because they have written A, right? So A stands for Arctics. Not going into that much detail like military and industrial. It depends upon the FPGA. We need to see the specifications for that. Now, so let us try to categorize our FPGAs. Okay. So basically, FPGAs are classified based on their processor support capabilities and each offering distinct advantages for different applications. Now, basically, I have divided these FPGAs into three types. One is without a processor at all. Okay. And another is a soft processor which is present, and another is a hard processor which is an SoC. Okay. So let us try to understand what do you mean by having a processor, what do you mean by having a soft processor, and what do you mean by having a hard processor with it, right? So let's say if I'm going to have a FPGA like this on a development kit or whatever the chip you are or whatever the card, basically we see it as a card. Okay, whatever the device you are going to have, you might have a network card, or in the day one we have seen, right, different type of network cards or router cards in the FPGA discussion, right? So let's say if we have a simple board like this and I have a FPGA chip with me, right? Now, you might have an FPGA chip without any processor, which is present inside that particular chip. Okay. Now, it is basically going to have pure logic implementation using LUTs, flip flops, and BRAMs and DSP blocks. Okay. So, this FPGA chip is not going to have any internal processor with it. This is one category. And the second category is soft processor. Now, what do you mean by soft processor is, let me give you one example of soft processor, what it is. Let's say if I'm going to have an FPGA like this. Now, this FPGA, some of the LUTs which we are going to have are utilized for acting as a processor. Okay. So we are not going to have a exact hardcore processor which is present inside this, but some of the portion of this FPGA is utilized for acting as a processor. Some of the LUTs are basically acting as a processor. This type of FPGAs are known as soft processor. We are not going to have a exact implementation using the gates, okay, for implementing, or we are not having a exact dedicated silicon area which is being implemented as a processor. But we are going to have an FPGA where the LUTs are utilized for developing a processor. Already, the libraries are developed by the Xilinx or whatever the FPGA which we are going to have. In that libraries, they have already developed this particular processor using the LUTs. This is nothing but our soft processor category. Is it clear for everyone? without processor and soft processor categories. Are these two clear? Okay, okay. Let us see with this particular examples. So FPGAs without any processor, where we are not going to have any processor inside the FPGAs. What is that we are going to have is lookup tables, flip flops, BRAMs, DSP blocks, IO resources. This and all we have discussed in our previous sessions also, right? And this FPGAs is not going to contain any processor. Neither soft nor hard implementations are included in this category. This is category number one. Okay. And what are the examples of this is Spartan series, Arctic 7, Intel Cyclone, or Lattice. Okay. This and all are the examples where you are not going to have any processor inside it. Okay. Now, what is soft processor? Okay. So basically, that is what I've told you, the processor core built using the FPGA logic using the LUTs and flip flops. Okay, so you're going to have an FPGA, and in this FPGA, some of the portion is utilized for implementing a processor using the LUTs and using the flip flops. Already, the developers has implemented a processor using this LUTs and flip flop, and this you cannot access. It is a processor. Okay, and it is synthesized like any other RTL design within the FPGA fabric, and it is capable of running firmware and software applications. Now, is it clear? So the difference between the soft processor and your FPGA with no processor, is it clear? Only one response. Yes, Ashish. Okay. Okay. Great. Okay. Now my very next question is, why do we need a processor? Can anyone tell me? In real life, like why do we need a processor? Sorry, I was not able to hear you. Your voice was low. For implementing the logics, okay. Main logics, okay. I'm expecting answers to understand the commands and to implement it, okay. To process the higher data, okay. See, so whatever the higher level abstraction level layers which we are going to have, like your OS operating system or whatever the things you are going to have, that yes, exactly, whatever the operating system or whatever the applications you are going to have, that is going to run in a processor itself. FPGA is not going to run all those operating systems and all. Okay, for running your operating systems or running your applications, you need a processor. Okay, that is where you are going to use a processor. Is it clear for everyone? Okay, if you want to develop or if you want to run your custom application or if you run your operating system, okay, then you definitely need a processor. That is where we need a processor, right? Now, so what are the some of the common soft cores is like your Xilinx microblaze. This is a very good example, and Intel based FPGAs and open source RISC-V cores. Okay, this and all are your soft cores. Okay, and the platforms Arctic 7 with microblaze and Cyclone with NIOS. Okay, so this and all you can see your soft core processors. Okay, and why do you need a processor and how you are going to establish the connection between your processor and your FPGA? For those, I have added some case studies where we can have the discussion there. Okay, yes, so this was about your soft processors. Now, next come your hard processor. So basically, a hard processor is physically implemented in silicon, not built using the LUTs. Okay. In the case of your soft processor, the processor was built using the LUTs, right? But here, in the case of your hard processor, it is not built using the LUTs. It is basically physically implemented in the silicon. Okay, and it is basically used for enabling higher performance and power efficiency. Okay, so here the hard processor is silicon implemented, physically fabricated as dedicated circuitry on the chip. Okay, and it is going to have higher operation frequency, and it is very power efficient because it is going to consume less power compared to logic based implementation, because it is an ASIC, it is not implemented using the LUT, right? So this is the difference between your hard processor and your soft processor. Is it clear for everyone? First of all, the difference between your soft processor and your hard processor, is it clear? Yeah. I'm coming to that particular point. Whether they are outside the FPGA fabric or whether these are inside the FPGA fabric, I'm going to come to that particular point, right? Now, let's say if you are going to have an FPGA, if you are going to have an FPGA with no processor at all, which is a only only a PL fabric, or it's a simple FPGA fabric you are going to have, then you need to have one external processor which is present, so that you can run all the OS layer applications or whatever the software layer applications you are going to have. You need to run this using an external processor, right? Now, if you are going to have a soft processor, generally the soft processor will be present inside your FPGA itself. Okay, so this will be your processor. Normally we are going to say it as PS. PS is nothing but programming system, and PL is nothing but your FPGA, that is nothing but programming logic. Okay, this is nothing but your FPGA, and this is nothing but your processor. And in the case of your soft processor, the LUTs are used for building this processor. Okay. Now, in the case of your hard processor also, in the case of your hard processor also, the same chip is divided into two parts where you are going to have PS and PL, but this PS is not built using the LUTs, but it is rather built using this silicon. Okay, it is physically implemented in the silicon, not using the LUTs. So that's why it is very power efficient and high operation frequency. And this is our PL, that is nothing but our fabric, our FPGA fabric, which we are going to have on the single chip. So are the three differences clear? FPGA with no processor, soft processor, and the hard processor. Are they clear? Uh, I think there are 23 people in this meet. If you respond, then it will be a good motivation. Like I will come to know whether you are able to understand or not understand, right? Yes, exactly. Okay, then. So this is nothing but my categories. So one is a FPGA with no processor at all, and another is soft processor, and followed by hard processor, right? Now, so this is one of the example of SoC FPGA architecture where we are going to have a PS, which is nothing but my processing system, and programming logic, which is nothing but my PL. Now, generally, the SoC FPGA which we are going to consider is Zinc. Okay, this is what we are going to work with in our course. Okay, so Zinc is going to have a ARM based processor in the PS section, and it is going to have a PL, that is nothing but our fabric, FPGA fabric. Whatever the Verilog code which we have written will be executed in this PL. Okay, please remember this. Whatever the Verilog code which we are going to write and implement, or configuration, the LUT CLBs we have discussed, right? That will be present inside this PL. Okay, and the processor, like running your instructions or running your software course, running your C++, C language, executing your softwares, applications, everything will be done over this processing system. Okay, and we are going to have something known as interconnect, which is going to connect your PS and PL. So it is going to look like this. So this PS and or our processor and our FPGA are going to be connected using one interconnect for connecting our PS and PL. Now, what is that interconnect? Generally, it will be using our AXI. Okay, we are going to use one protocol which is known as AXI protocol for connecting our processor and our FPGA fabric. Is it clear? So in hard processor, LUTs and all are not connected with the processor. Yeah, that is what I've shown you, right? So this fabric PL is going to have all the LUTs and CLBs are connected to the processor using this interconnect which is known as AXI. Have you heard about AXI? Anyone heard about AXI protocol? Have you heard about AXA protocol anywhere before? Yes. So this is where we are going to use our AXI protocol, and we are going to use something, this interconnect, for establishing the connection between our FPGA fabric, you might say your CLB LUTs, with our processor. Okay, using this AXI protocol, we are going to connect it. How to connect it, how to write our test cases, how to write a software code, and how it is getting connected. That and all we are going to learn in our course. Okay. So is it clear? The categories, are they clear? And how we are going to connect, are they clear? Yes or no in the chat box? Yeah, great. Okay. Yes, yes. Now, what are the categories of SoCs which are leading is Xilinx Zinc 7000 and Zinc Ultra Scale Plus, Intel SoC, Microchip, Smart Fusion. Okay. So these are the categories which we are going to have, where you are going to have PS and PL fabrications, right? So this is what we are going to have. Now, here the main thing need to which we need to understand is modern embedded systems integrate processor, FPGA, and peripherals on a single board with clear connectivity patterns. Where we are going to have a processor, that is our CPU, and we are going to have a FPGA, we are going to have HDMI ports, UART ports, USB, Ethernet, everything on a single chip, right? Now, first of all, before that, can anyone tell me what do you mean by system on chip, SoC? What is an SoC? System on chip. What do you mean by system on chip? Yeah, basically you are implementing a CPU on a single chip, right? Exactly. Okay. Yes. Now, the question comes like we have discussed it, right? What is the responsibility of your processor? So it is going to control overall system. It is going to control your peripherals, everything, and it is also going to execute the operating system. If you want to run your Linux or RTOS or any other application, you definitely need a processor. Okay, and you are going to if you want to handle all your peripherals. Normally, in most of the SoCs, if you are going to the zinc based SoCs, your processor is going to handle all these peripherals. Okay, and if you want to run this GUI, what is GUI? Anyone knows? What do you mean by GUI? Graphical user interface, right? Whatever the screen you are seeing, right? So for running those particular programs and everything, you need a processor. Using a simple FPGA, you cannot do all these particular things, right? So you need a processor for this particular things, for system controlling and for operating system and for peripheral handling and for running your GUI programs and applications. You need definitely a processor. And for configuration of your FPGA also, depending upon the architecture, we are going to use our processor. So these are my processor responsibilities, right? Now coming to FPGA responsibilities. So I am going to use it for high speed data processing or custom hardware acceleration or CPU offloading or deterministic real time logic. Okay. So in this particular cases, I am going to use my FPGAs. Okay. So these are the roles of my FPGAs and the processor. Okay. So is it clear for everyone? Any doubts or any queries in this? About your introduction to the different categories of processors and different type of FPGAs. So in our next session, hopefully on Monday, so we are going to start discussion of different type of cases where we are going to take a FPGA without any processor, okay, and we are going to see how we are actually establishing or how we are configuring the FPGA. What is the boot up process which we are going to do? What is the thing, how to activate your processor or how to establish the connection? That case one we are going to see, and case two is we are going to have a soft processor. Sorry, we are going to take a hard processor itself, and taking the hard processor, we are going to consider how to establish the connection, how to initiate that particular FPGA, and all we are going to see, right? And next, after that, we are going to, okay, this is the plan which I'm going to have, and after that, we will see. Okay. Yes. So that's about this particular session. Okay. Basically, on a single chip, we are going to have our processor and our FPGA, right? Let me share my screen. 1 minute. On a single chip, I'm having my both processor and my FPGA, right? So if this processor wants to communicate with this programming logic or FPGA fabric, like let's say suppose if it needs to send any data, okay, to my programming logic or fabric, so here your interconnect is going to help you. Okay, this interconnect like AXA protocol you are going to use, and you are going to send or receive whatever the data which you want to send or receive. Like for example, your peripherals. Let's say this is my FPGA chip, and this chip is going to have my processor and FPGA fabric. Normally, all the peripherals like Ethernet or UART, or you can say HDMI, okay, everything will be connected to your processor itself. Now let's say if your fabric, whatever the RTL code you have written, needs the data from this UART, okay, who is going to give you? The processor is going to give you. The processor is going to take this particular data, and using the interconnect, the AXI interconnect which we are going to have, it is going to push that particular data to our PL. And after computing the data which we have received, and if we want to give it back to the processor, we are going to use this AXI interconnect. Is it clear? FPGA fabric is exactly the thing which we have discussed, right? The LUTs, the CL base, whatever the things which we have discussed, right? TIDMC. What is this TIDMC? Sorry, I cannot understand what is TIDMC. Yeah.